Here's Integrated 3. It's your Part 2, Lecture 10.1.1. We're going to do problem 10-4. So it says, when an arithmetic series has many terms, adding them one at a time can be tedious. Having other strategies to calculate the sum is useful. To look for a strategy, consider a new situation. Flo is preparing to run the 100-meter race at her next track meet. Her coach decides to collect data to see how well Flo is accelerating at the beginning of the race. The sequence below represents approximately how far in meters Flo travels during each second of the first 6 seconds of a practice race. So it gives you a little sequence. Write an equation. You probably already looked at my equation. And so I've got this all written down. So to write an equation, I realized that it's arithmetic because it's adding 2 each time. That means it's linear. So if I think about y equals mx plus b, then m would be my slope, which is 2. And I prefer this method right here because that's like y equals mx plus b. I do have to go backwards by 2 to find b. So 1 take away 2 is -1. But if you prefer this way is also nice because you can use your slope and then you put n minus 1 here, and then this is your first term. And if you want to check and make sure that they're equivalent to each other, you can go 2 times n is 2n, and 2 times -1 is -2. Well, -2 plus 1, that's -1, so they're the same, and you can put numbers in just to make sure they work. So letter B says, what does the related series represent in this situation? So remember, this is like how many, is it seconds? This is her rate at meters per second. So it takes her a while to gather speed. So she starts out and she's going 1 meters per second, but then by the second she's going 3 meters per second, and then 5 meters per second, 7, like that. So when I add them all up, well, I guess that's the total seconds, or sorry, the total meters that she went in the race. So this would be the total distance of the race. Oh, this is how far she goes each second. So that was 1 meter. I mean, she is gaining speed, but she went 1 meter, and then the second she did when it's going 3 times as fast because she went 3 meters, and then 5 meters. The 4th second she went 7 meters. The 5th second she went 9 meters, and the 6th second she went 11 meters. So yeah, 1, 2. So if you add them all up, it's the total distance in meters. And then it says Flo's coach decides to use these square tiles as, oh, can you see them? The square tiles as shown in the diagram below to represent Flo's distance from the starting line as time passes. So that's what we were just talking about. Flo's coach arranges her tiles on a graph like the one at right. How are the terms of the sequence shown on the graph, and how is the series represented on the graph? So this is each second of time that goes by. And this is her rate. Okay. So determining the area of the long rectangle Flo has made, determining the area of the long rectangle Flo has made in part C, this long rectangle. If I wanted to know the area, it would be length times width, right? So I think I could just count the boxes. Yeah, and that's what it says. You'd have to add all the sections. However, if the columns in Flo's graph can be rearranged to form a single rectangle, its area can be calculated more easily. Discuss with your team how this can be accomplished and be prepared to share your ideas with the class. Well, I can't write with pen in my book, but I'm going to go ahead and, my idea is to, if I shared this in the last video, if I take this 11, this long, tall rectangle, and stack it on the shortest rectangle, then over here, well, it's going to be a lot taller though. It's not going to be a lot taller. It's going to go up to 12. So this one, I'm going to stack it over here, and it's going to be, if that's 12, it's going to be up there. And so now it's gone. And then I take this next to the last rectangle, and I stack it here. Well, there I've got 3, but then I'm going to add 4, 5. What do you know? It's going to stack up to 12. I'm gonna shade it in so it looks a little better. So what I'm doing is I took this rectangle and I moved it, and then I took this one and I moved it. So like I'm covering them up with my thumb because I'm trying to tell you that they're gone. Well, they're not gone, but I moved them over to here. And then if I just take this white rectangle and put it on top of this one, it's gonna add to 12. Okay. So now I'm covering these up so that you can't see them. So now I have all the 3 triangles that are on the right hand side. I've stacked them onto these, did I say triangles? These 3 stacks, I stacked them onto the stacks on the left hand side. So now I've got 3 stacks that are 12 high. So 3 times 12, and I'm getting 3 times 12 is 36. Should we count? I don't have an answer key. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, there's 36. So now, like, it's just easier if you do it that way. And then for the next, so that's just a way of, it's like a strategy for adding up a series. So let's practice on this one. Calculate the sum of the arithmetic series by the graphs below, and how can you tell your answer is correct? So this one would be, the area would be 7 times 5, so that's just 35. This one, we're going to use that stacking method. There's 16 stacks, I suppose. And then this, the tallest one is 10 and the shortest one is 4. So I know that when I take this 10 and stack it with this 4, I'm going to have stacks that are 14. All of these, they're going to end up being pairs of 14. So then I would just go 14 by, well, it's going to be half as long because I'm taking half of these and stacking them over here. So 14 times 8, and that's 112. And so I think I ran out of time, but basically you can add the first the first number to the last number and find out what it is, and then multiply it by n over 2, or however many numbers there are over 2. And then later on there'll be a math notes box about that. Should I go ahead and look at it? I'll let you guys look it up.